so many of them. Recorded. This is all good. Okay, so there's a cliff in Greenland. I took that picture out of a window of a helicopter with some senators in the helicopter. It was all fascinating. So thank you so much for all of you to showing up here, and especially thanks to Tavi. She has done wonderful things. The rest of the organizers here. A big thank you to the International Glaciological Society, and thanks to all of you for tuning in. And so we will see what we can do. As some of you know, I'm an old fart. I grew up on the wrong side of the tracks. I went to Ohio State because I could afford Ohio State. Ohio State was fantastic. The people there were really, really good to me. Wonderful people. I saw Julie Palais was logged on. Hi, Julie, thank you. This is a picture of me summer after my freshman year. Those are NSF Spry TUD radar records, and I'm drawing lines on them. And I'm doing that for Ian Willens, who is shown here on a dry run of the Taisag field trip up to Kelly's Island. That was my first scientific meeting, and he went way too early. He did really good things. My sophomore year, David Elliott, shown right here, took me to Antarctica on the Hero. I got sick all over the Hero. Oh my goodness! But what a wonderful, wonderful experience that was. Right? I have been with the IGS a long time. My first scientific meeting was with them. I actually just looked. I've had co-authorships or authorships on more than 70 papers in IGS publications. And, you know, I've got an H index in the 30s just from IGS. They have been really, really good for me. We owe them a lot. And that's true. I do have the IGS tie and I do have the IGS dish. So if you haven't gotten your stuff, they're out there. Big thing is to keep your membership going and go to the meetings, right? I'm really fortunate because I've had just such wonderful colleagues and friends all the years who have taken care of me and allowed me to play along. And that's really the strength of my career. This is Sridhar's expedition to Thwaites Glacier. I'll show you some of the data from this trip later. You will notice I'm not in there. I've been to Greenland 9 times, Antarctica 4. I spent a year in the freezer in Denver and a few other things, but I'm a lightweight compared to most of you. So current grad students, fantastic people. They're going to go great places. Keep your eye peeled. A few former grad students of many, right? So Kaya over here and Nate here crawling around in caves in Svalbard, the very photogenic place to get former grad student pictures. A few colleagues that I've collaborated with for more than 20 years. Byron Perzak over here, Dave Pollard, Don Voigt, you know, Todd Sowers down there, more than 20 years. Yeah, wow. Yeah. And new people coming, and keep an eye because the new people coming to Penn State who are interested in ice are going to do great things. And so I'm really happy to say that the future is in really strong hands. Sridhar, I soldered pieces of seismometers together for him in 1985. I've relied on him ever since. We've been collaborating since grad school. This is a GISP too, for what it's worth. So at any rate, and my family, my dear wife is going to help us show slides a little bit later. So she's sitting right here. She studied with Ian Willens. She was a librarian. Now she teaches quilting. Our elder daughter is a science teacher. She's department head. She's also a mother. Our younger daughter is a professor at Manitoba, and I'll show you some of her work later, which is really important, actually. So you know, I've got a job because I have good friends, and it's that simple. Right? So at any rate, in the course of doing this, I got to help the Ipcc. I got called in to the second assessment, because there was a bit of a fight about West Antarctica, and I had helped write a review on that with Ian Willens. So I was involved fairly early in the game. The Ipcc, in some sense, is the mother of all committees. If you took all the reports and all the pages and you printed them out in old style, they wouldn't fit under the ceiling in this room if you just piled them up. if you tried to take everything the IPCC did and turn it into a tweet or two, right? I don't tweet, but if I were to try to tweet the IPCC, it would be something like this. Imagine two futures, one in which we pretend we scientists are evil liars, we ignore what we know and do business as usual. Another one in which we use our knowledge efficiently. The future in which we use our knowledge efficiently has a larger economy. This is Bill Nordhaus, 2018 co-recipient of the Nobel Prize in Economics. He built the tools that allow you to say this with absolute confidence. We would have more jobs, we would improve our health, we would increase the security of our nations, and oh, by the way, we'll have a cleaner environment and we'll be more ethical. Right now, if you are the hardest nosed business person, or if you are the greenest tree hugger, the future is in the same direction. And that is really an amazing thing. Using our knowledge helps across the board. Now, someday, if you want, invite me back and I'll give you this story. But it's a different one. But we, as ICE people, have a role in this, right? What do? We have to get the processes for the projective models. We have to get the history for the model validation. We have to look at what the impacts will be. We have to look at how we can adapt to this as well as mitigation. And this includes people doing snow. It includes seasonally frozen ground. It includes permafrost. It includes river ice and lake ice and sea ice and glaciers and ice sheets. It's what the Glaciological Society does. And what you people sitting out there do really does matter. And it matters a lot. Okay, so I used to work a lot on climate history. I got to go to GISP2 a few times and look at ice cores and what have you. If you were going to give this talk on climate history, I could give you that one too, right? Okay, the big picture is really sort of amazing when you look at climate history for the big picture. It is a major conclusion that climate is affected by a whole bunch of things, but CO2 has been the biggest control knob in terms of something that matters, that has changed a lot. The modern models that are projecting climate change and climate impacts are actually pretty good. But if they have a flaw, they are overly optimistic. The actual changes are either what they model or the actual changes were bigger, faster, less expected, more damaging. There's no serious evidence that climate scientists are overly scaring people. There is some evidence that we're not being scary enough. Okay? And that's an important point. For what I'm going to talk about today is sea level, and it is the same story. Either the models are really good, they're getting it right, or the models are overly optimistic. They're not being as scary as they could be about what will happen if we don't use our knowledge effectively. Okay, so here's the data. You've seen this a lot. This is a triumph of scientists and engineers working together to do things. This is the history of altimetry. You can go look at it right up to date. Sea level is rising. Now, I can tell you, and this is absolutely true, I used to get calls from government persons who said, "Why are you lying about sea level rise?" And then they shut up. And then they said, "Why are you lying about sea level rise?" All right, this is El Niños and La Niñas moving water onto and off of the land. Those cannot be a long term because once the lakes fill up, they run off. Okay, and this already matters. You may have seen this. I swiped it from a source down here, used under fair use. This is not a storm, it's a high tide. This is not a canal, it's a street. This is a road, you know, that's where the car comes in. This is what they call adaptation. You put up a no wake zone sign in the middle of the street when the tide comes in. This is a parking garage in Miami. This octopus was not thrown here by hockey fans, it swam in. So far, this is not that expensive. They call it nuisance flooding because it's a nuisance. But at some point, that nuisance is going to get really expensive. And this is an important point, that it is fairly clear that the damages to people, the dangers to people, the dislocations, the costs are superlinear. They go up faster than the sea level does as nuisance flooding becomes, this really hurts people and it's really hard to fix. You can see that here, right? This is a hurricane that did not get into New Orleans. I would not have wanted to be the peace officer over here, but if we don't do things pretty fast, enough sea level rise to get over this is almost baked in already. But what we're going to talk about here is the possibility that it would disappear out of the picture. And what do you do with that? All right, so that's where we're going to go today. The people working on this are really important. The people getting the snowfall and the surface mass balance and the thermal expansion of the ocean and all that right are really important. But then we're going to add this ice sheet collapse bit. Okay, so let's go back to the sea level record. Let's squeeze it down. The Ipcc did this. So the previous plot is now this little thing here. Add some history. Yes, sea level rise has accelerated. Add some futures. Our decisions are the single most important thing by the time our students are old. Our decisions are the most important thing here. Okay, and that's what you see here on these projections. But what we're going to talk about is whether it could be higher than that. What's going on there? It is human-caused warming that is driving the sea level rise. Crudely, fuzz your eyes. It's sort of kind of a third melting of mountain glaciers and dumping water into the ocean. It's a third the ocean expanding as it warms. It's a third from the ice sheets, mostly from melting on top of Greenland. Maybe a little coming out of groundwater that we're pumping too fast, but a little is being put on the land behind new dams, and that sort of balances. So the detailed balance among these shifts over time. Ice has been becoming more important as it has warmed. Okay. But when you go forward, if that balance still matters, we're happy. We're lucky. Things have not gone to heck in a handcart. By the time you get sort of a third of a meter of sea level rise from the mountain glaciers, they're gone. There's no ice left in the mountains. They can't raise sea level. The ocean, it depends whether you're warming the cold parts or the warm parts because of the thermal expansion is temperature dependent, but you don't get too much rise out of a degree of warming in the ocean. The ocean is only a couple degrees warmer now than it was during the Ice Age. This is not a big term down here. Greenland, more than 7 meters, Antarctica, a whole lot. So really, the question about high sea level rise is a question about the behavior of the ice sheets. The Ipcc high-end projections for 2100 have less than 1% of the ice sheet sea level equivalent going into the ocean. Strong warming, they leave more than 99% of that sea level equivalent on the ice sheets. It is really, really hard to make a future that is better than that. It is really, really easy to make a future that is worse than that. Because if you get a few percent of that ability of the ice sheets to raise sea level, the projections are out the window. Okay. This is the Hunt-Lennox globe, circa 1510. It is this beautiful copper thing. It is probably the second oldest known globe that has the Atlantic basically right. It was copied from the oldest, which was an ostrich egg. It was etched on an ostrich egg, probably. And this particular one happens to have on it the famous phrase, Hixent dracones, here be dragons. All right. So in my title, I talked about dragons. This is maybe the first appearance of here be dragons. And it's over there next to the other side of Asia, actually. And it might have been referring to Komodo dragons. No one's sure. But it's this interesting thing about knowledge. If you don't know anything, you don't know anything. When you learn a little, you don't know what else is out there. And so when you're ignorant, you sort of say, well, maybe there's bad things. Maybe there's dragons. Sometimes there really are dangers. Usually there aren't. And our job, we're the explorers, we're the people who are supposed to find out whether there really are dragons waiting for us in a warming world or whether there aren't. And so that was my conceit here. So and the job ultimately falls to the IPCC to take what we learn and assess it and assimilate it and make it useful for the public and the policymakers. So I'm about to do something that you could call IPCC bashing. I am not bashing the IPCC. I have great respect for the IPCC. I am proud that I helped a very small amount. I missed a lot of family things growing up because it was midnight and I was trying to get Jonathan Gregory something about sea level rise. You know, we sweated for the IPCC. There's absolutely no evidence that they are alarmist. It's not there. There is some evidence that they are overly conservative and things could be worse. And I said that before, I'll say it again. If they are erring, it's on the side of low. And if you haven't seen the Oppenheimer-Oreskes book, take a look, it's fascinating. There's a link, there's no link, but there's a title down there. This is something from Andra Reed Gardner. She actually studied across the street from me at Penn State. I was on her committee and she's gone on to do great things. This is a history of projections of sea level rise. And the IPCC is the purple bands and then the brown bands going along against time. So when was the projection of sea level rise made? And the IPCC is in purple and brown. The IPCC reflects the underlying literature. Everything else on here is the underlying literature. And what you probably notice is that there is a tendency, if you wanted to complain about the IPCC, you would say they're too low. And you might ask, is there really basis for the low end of their projections if this is the underlying literature? So just put that in mind. This is a summary of literature that does not prove that these are right, but it raises an interesting question. Something from Stefan Rahmsdorf, and then he did this again, and there's been a few other looks at that. The IPCC central projection for sea level rise, and the uncertainty range, and what actually happened. And it isn't wrong. What happened is just barely within the upper bound of the uncertainty range. But it's not one that you'd celebrate how well you did on your projections, and what's been happening is on the high end, not the low end. So those are hints that maybe we could see higher sea level rise than in the IPCC range. How could that happen? And I want to make a really important point here, which is you do not need new processes. Things that we have known about for a very, very long time happening in new places are sufficient to put the top off of those projections. There is a real risk of additional processes turning on, but you do not need them. And I'm going to walk you through this old story, and it's an old story. So in the pre-COVID days, you could go to Alaska and you could get a cruise ship and you could drive 100 kilometers up Glacier Bay and go watch little tiny weeny glaciers making little tiny weeny icebergs way up at the head of the bay. Beautiful place. I have been there. It's wonderful. It's very much worth a visit. When Vancouver went by in 1794, there was no Glacier Bay. It was full of ice all the way out to the front. When John Muir went by in 1888, it was mostly open. And in that century, less than a century, most of this opened up. And the total retreat has been more than 100 kilometers. I'm going to show it to you from above, from looking down, and icy straits at the bottom, and the bay is up in here. The ice had advanced way out to this bottleneck, this little narrow place, both vertically and horizontally narrow. And you had this big bottle of ice up here, and it was trying to drain out of the little neck out here, like shaking catsup out of a catsup bottle or something like that. And then probably from warming on surface mass balance, it retreated a little. And then it lost the stabilization of the bottleneck and it went beep, and it ran back. And Muir saw it back here, and it was back here when John Muir was there. I'm going to take you to that little pink box up at the top, and we're going to look at it there. So this is a little tiny corner of the retreat. And this is what that looked like in 1941. The calving front was right down in the lower right-hand corner there. And if you went back to the same rock 9 years later, it was there. And you go back to the same rock a little later, and it's around the corner. And it's sort of watching a car wreck. What can I say? You know, that was that little corner. What happened to the thickness? Beautiful paper here, good folks. And this brighter red up here is thinning of 1,500 meters. So you can now take your boat up there. And that was under 1,500 meters of ice. A mile of ice is gone. It did not go away by flowing out the bottleneck. It went away by the front calving back to it. So this is long been known. Marine ending ice tends to stabilize in the bottleneck where the fjord narrows either horizontally or vertically, and usually both. There's a whole bunch of processes that maintain that stability. If you try to perturb it, it hangs on. If you succeed in perturbing it, it retreats to the next bottleneck. Normally, it's in a narrow fjord, and the next bottleneck isn't too far away, so the event is locally spectacular and globally insignificant. If the same thing happens in parts of Antarctica, it is globally significant. And that's where we have to start, is just the same process that we've seen over and over in the Laurentide and the Fennoscandian and Svalbard and South Greenland and Chile, and those same processes acting in the big basins of Antarctica matter to the world. This is one demonstration of this getting hung up on a bottleneck. This is not the first, it's not the last, it's just one. We published this in Science after Sridhar made some great observations. The models are from Byron, from Dave Pollard, and from Todd DuPont. And I'm going to show you retreat. This is ice right here, and this is air up over the top of it, and there's water on the edge, and we're looking at a vertical section. And I'm going to show you the retreat. They're identical, except the one in the bottom has a little bottleneck. It has a bump. And the ice jumps to that, and then it hangs on for dear life, and it's not retreating, and it's not retreating, and it's not retreating, and it's not retreating, and then boom. And that's a horizontal bed. There's no Misi or Miki or anything in here. It's retreat from a bottleneck. So if you go to Antarctica, you know this thickening where this one slowed down and reds are thinning. And we're going to go worry about Thwaites Glacier over there in the corner. And here's bed map 2. And the deep blue is 2,500 meters below sea level and 1,500 meters above. So it's really thick. This is the West Antarctic Rift System. If you have been to Nevada, this would be the Sierra Nevada over here on the right, and this would be the Wasatch Front on the left. You could do something with the East African rifts and make it the same way. The ice wants to flow along the rift, but it's a long way to get out. And because it's a long way to get out, it had to build up in the middle, and then it leaks out the side. And so Thwaites Glacier is a very strange place that it's rushing out a little gap in the rift flank when the ice wants to go the other direction. And in doing so, it's coming up, narrowing vertically, it's narrowing horizontally. And there's a different view with the bed from Knut Christiansen, and a possible analogy on the left in the pre-COVID days. That traffic jam is not bad enough because it's only horizontally narrowing. We should have a vertical narrowing as well, another deck or two coming in, because that's what really goes on. And so the flow is jammed up at the mouth of Thwaites simply because it has to get out of that little shallow, narrow mouth. If it retreats, that doesn't apply. If you were to retreat out of there, you could thicken it as much as a few fold, 500 meter below sea level to 2,500 meter below sea level. You can widen the front a few fold. If you just keep the same velocity, you will now have a significant effect on projections of sea level rise because it's so much bigger. Now, in fact, you're virtually guaranteed it will also speed up, and I'll come back to that. But all you need is that cross-sectional area, and you get a lot more. And here's one version of this from the model by Rob DeCanto, Dave Pollard. I had a tiny role in this way back, but surely not much. While Thwaites is converging, it's a fairly narrow calving front. These light colors indicate a shallow grounding zone. If you kick it off of the sill, out of the bottleneck, you get a very much wider zone, and the deep blues indicate that it's deeper. There's new modeling has just been coming out that is well worth a look. If you lop off the ice shelves, you do get a whole lot more sea level rise. And it's not yet by kicking in any instabilities, any new physics. It's just pull it out of that bottleneck so it's really wide and really deep, and it's dumping icebergs. A review we did, Ian Jock and Dave Holland, a number of years ago, two broad pictures of the world. If you have both cold air and cold water, you tend to have ice shelves. As I'll show, the ice shelves are always holding back the ice. The ice is stabilized in a bottleneck where it's narrow and usually where it's shallow. If you warm either the air or the water, you tend to lop off the ice shelf and retreat to the next bottleneck. Beautiful piece of work here. First at all, Nature Climate Change 2016. Everything in color is an ice shelf. The darkest blue is the ice shelf is not holding anything back. The light blues are not holding much back. There's virtually nothing here that is completely unconstrained ice shelf. When the ice gets past the last buttressing, it breaks off, which says the ice needs that buttressing to have an ice shelf. All of the grounding zones, there's a whole lot of buttressing, which means the ice shelf is holding back the land ice, making the ocean smaller and the land ice bigger. Okay. And so this one is important in several ways. One being that if you once lose the buttressing on ice shelf ice, it does break off. Another one is that has to influence the flow of the non-floating ice. I keep going back to Doak et al. 98, and they said the same thing, basically. This would have been light blue in the previous picture, and this would have been browns. And they said, this is the Larsen B ice shelf. And they said, if you once break into the ice shelf that really is holding things back, it'll keep breaking. And so they essentially predicted the collapse of the Larsen B ice shelf. And we all know what happened. So here's the Larsen B ice shelf at a slightly different orientation. Ocean over here, ice shelf here, meltwater ponds on top of it, wedging into the crevasses. It broke back into that buttressing ice, and then it broke away. The calving rate was something like 10 kilometers a week. Right, it was pretty fast. This is brittle control, not viscous control. And the thing broke away. That, of course, did not raise sea level, but the tributaries sped up, as much as 7 or 8-fold. And so you get sea level rise from that because it was holding things back. We don't go to Alaska to study ice shelves. We don't go to South Greenland. We don't go to the northern Antarctic Peninsula because they're all gone, right? Ice shelves are almost always in really cold water under really cold air. If you warm the air, you can melt water wedge. There's interesting physics and drainages that don't break it apart, and surface drainages. It's this wonderful world of things we need to understand. You can also lose the ice shelf when the ocean warms, even if the air is really cold. The Heinrich events rather clearly are ice shelf loss events, and I can go into that later if you'd ask, but they are pretty clearly ice shelf loss events. H2 is the absolute coldest bit in the air in the ice age, and yet you lose the ice shelf and have a surge. So it's pretty easy to have warming ocean take out ice shelves as well as warming air. And there seems to be pretty strong hysteresis in this system. We have seen a lot of ice shelves lost. We haven't seen one permanently regrow, we've seen fluctuations in conditions, it is harder to get it back than it is to lose it. They must have formed, so we know they can form. We know they're trying, but so far we've seen losses and not regrowth. Okay. I sort of kind of suspect that the ocean warming will be the more important, although I'm very, very interested in the work on the atmospheric warming. And I'll show you some of the pictures from Greenland of what ocean warming has done. This great new paper, if you didn't see it, have a look, that is showing these, we're on the same path. And so what happens then is more or less here. This is from Ian Jockin et al. I helped a tiny bit, but we're looking down on Jakobshavn. This is the melange out here on the left. This is the ice shelf here, and rock is up there. And what happened is the ocean warmed, David Holland's work. That warm ocean, it had been maybe the world's fastest glacier. The warm ocean thinned the ice shelf. That reduces the friction. It lets the ice go faster. That breaks it on the sides, so you get these fractures along the sides. Eventually, it breaks completely, and then the whole shelf broke off, and what had been maybe the fastest glacier on Earth doubled or tripled its speed. And it was warming ocean that really kicked this one. Big shameless plug for Karen Alley up in Manitoba. Work by Mark Fonestaki and Jockin, and then Kaya Riverman and Knut Christiansen and Sridhar and others. Ice streams have troughs in their shear margins for very good reasons. When those troughs reach the ocean, they float up and you get troughs in the bottom of the shear margin. When you warm the ocean, that's where the plumes go. And that knifes up into the sides of the ice shelves and makes it really easy to break them off. So the ice shelves are preconditioned to go away. And that's not good news either. We're losing mass from Antarctica right now. We're losing mass from Greenland. That tends to freshen the surface ocean. And that's also not good news. It could cool things off and maybe damp down the meltwater and crevasses. But if it does, what happens now is the warm waters offshore tend to follow isopignals and mix up to the surface offshore. If you put a freshwater cap on top of the ocean from mass loss coming off of the ice sheet, the isopignals tend to bend over and they hose hot water against the grounding zone. And so, yes, you may be saving yourself from crevasses above, but you're going to kick it from below. And this is probably the story of the Heinrich events. It is a worry going forward. Okay. So ice shelf loss in a warming world, either ocean or air or both, huge problem. That is the single biggest forcing that is likely to hit the Antarctic in the near future. It is a forcing. It will tend to destabilize the ice. But now we have this real question, will it truly kick the ice off of the bottleneck? Could the ice hang in the bottleneck and we're okay? And that proves to be this wonderfully complicated problem that people are just, they should be headed for the field right now to solve it, but COVID has kept people home. But the Thwaites Glacier folks, I'm going to show you a little model. This is flow line. Air is up here. Ice is in here. Rock is down here. And this is something Byron published in 2013, which a bunch of us. Other people have done this. They're getting the same sort of answer. On the left, we have a linear viscous bed. On the right, a plastic one. And the linear viscous bed allows the loss of buttressing from the ice shelf to thin near the coast. It floats off of the bottleneck and retreats. And in this one, the bed controls, and on the left, watch it, you just collapsed. And on the right, you didn't. But if you do make the one on the right collapse, it goes even faster than the one on the left. All right. So this gets really interesting that the near future behavior may depend hugely on the nature of the bed and its shape, but also its flow law. With a viscous bed, you retreat easily from the sill, but then you retreat fairly slowly. With a plastic bed, you have more difficulty kicking it off, but then you retreat faster. As I'll show you in a moment, the real bed actually looks like it's alternating, viscous plastic, viscous plastic. And Stephen Kollner, working with Byron, did some really simplified models, beautiful work. And he found that sometimes viscous plastic is just between the end members. And sometimes it's more extreme than either one. So you actually have to do this right. And that's going to be hard. So let me show you just a little bit of what we've been learning about this and how hard it's going to be. Go back to West Antarctica. And here we have the ice draped over the top, the flow lines, and we have bed map underneath it. And Sridhar and company went down and they did some geophysics down here. And I'm going to take you to this one little box right here. It's a nice little box. This is what the bed looks like. Right, this is 10 kilometers down here. This is swath radar. John Payton, Nick Holshoe, hi Nick, Knut Christiansen, and Sridhar. This is just groundbreaking. It's just wonderful. It's revolutionary. The total relief of the bed in this grid is 700 meters, 700 vertically. These flutes in here are 100 meters high or more, and they're 15 kilometers long, and there's these big troughs eroded in the front of the bedrock bumps. You could just look at this all day. It's just truly changes our view of how the world works. And the ice flows across this lubricated stuff, and then it rams into these giant bumps in front of it. And we have to sort of get this right. Atsu and Lizzie, working with Sridhar and company's data, can actually tell you what this stuff is. And these are bedrock, and then this is till, and then it's bedrock, and then it's till, and then it's bedrock, and then it's till. And it's alternating one and the other and one and the other. And it really, what we know about bedrock and till, that would be more viscous, more plastic, more viscous, more plastic. Doug McHale and also Luke Zoot and Byron Perzak have been doing some modeling. Flow is going the other way now. Sorry, we reverse flow. But if you think about flowing across the till and then against the bump, what do? You get this big high pressure zone. If you then ask, what would that high pressure zone do to the water? It would squeeze it out. Well, what would that do to the till? You'd couple into it and sweep it away so you can erode those troughs. And now we're actually going to have to get the pressure fluctuations right, to get the till in the water right, to get the lubrication right, to find out whether the ice can hang up on that bump or whether it'll retreat from it. It's a real challenge. So at any rate, whether losing the ice shelf will really cause the retreat, I think is still an open question. We got to get it right. And there's some work to do. Then the last little bit, and then we'll sum up here. So far, you go to the front of a glacier where it's got a calving cliff, and you watch the YouTubes of the giant icebergs rolling over, and it's obviously brittle, it's breaking. So far, though, it looks like the rate control is viscous. It breaks off a little too thick to float, then it thins to flotation, and then it breaks off. And yeah, it may break a few, and it might then pass flotation, and there's a whole lot of wonderful detail of this that is being worked out, and it's really, really nice science. But so far, it really does look like, even at these huge calving cliffs, that the control on the rate is viscous. Now, there's a real possibility that if we retreat in weights and you go back into a place where right now the ice is almost 4,000 meters thick and the bed is 2,500 meters below sea level, that you will switch to a brittle control or rate control. And this goes back to Hansen and Hook, Jeremy Basis's work, Dave Pollard and Rob DeCanto, Byron et al. I would note that if you put in the Clerc et al. Rate loading thing, the existing models are static, so adding rate loading will make it break faster, not slower. It's an interesting thing. But at any rate, it's fascinating paper and well worth a look. You can get a huge amount of sea level rise without switching to brittle control, without switching to Mickey or marine ice cliff instability. But there still is a real chance that we will have marine ice cliff instability because the stresses will get really high. okay? So the fastest sea level rise without brittle control in the sun et al., it's a great paper if you haven't seen it, brand new out in Journal of Glaciology, is almost up to DeCanto and Pollard. DeCanto and Pollard is not even vaguely a worst case scenario. They limited calving greatly. And it is possible we could get things that are a lot faster than that. Okay? So let me frame something here. As I said, I'm old. My PhD, I went to Antarctica. We collected cores. I was going to do petrography, cut thin sections, do geology on the cores. Gave them to the NSF contractor. They melted my PhD on the way home. This was not a good day when it got home. I ended up with a very short season in central Greenland. I went back south and got more core. The Navy flyers were getting ready to go to Greenland. They wanted to know from me, because I'd just been in Greenland near the summit, whether they would find crevasses. The Air Wing commander invited me in, and he said, I'm going to Greenland, will I hit crevasses? And I did the science. And I actually think I did the science okay. And at the end of doing the science, he said to me more or less in these words. He says, if I fall in a crevasse, I will get out. And I'm going to come find you. And I'm going to put your reproductive organs in a vise. I'm going to set the table on fire, and I'm going to give you a butcher knife. Now, will I fall in a crevasse? Right. These days, I'm an old, slow, careful, not at all excitable person. In those days, I was excitable. If you'd have had a blood pressure monitor on me, you'd have just taken me to the hospital. I gotta tell you. And it suggested that he'd take out a little insurance and do a ski drag. And of course, he was gonna do that anyway. But when somebody says, are you sure? I sometimes have that running in the back of my mind, right? So I'm not sure that we will get large sea level rise. It may not happen. But it is plausible based on physical processes that we observe now. And it is possible based on known physics that we haven't seen at scale. Under strong warming, we're going to cause more warming faster over more ice than nature ever did. Paleoclimate record, the warmth arrived on orbits over 10,000 years. It didn't arrive on RCP 8.5 over 100 years. We could go way outside the calibration data set. And we've got to consider things that go outside that calibration data set. And so, you know, can I look at the commander or the people or the politicians and say they're safe, that there's, no, I can't. And so, yeah, it's hugely important. It's really fun scientifically. It might be a stuffed dragon. It might not happen, but there might be a real dragon out there. And it matter what you do, this matters. It's important because the difference between 1 meter and 4 or 5 is large. So with that, I'm gonna switch gears, and we're gonna close this up in about 4 minutes, and my dear wife is gonna help here a little bit. You might have figured out I'm a professor. The kids used to say that I had a professor button, and they'd say, oh my goodness, you just pushed his professor button. He's about to profess, stand back. Right, so I'm going to review here just a little bit for you, and we'll get through the review, and we're going to do the review in G major, right? So she's got the clicker, and I'm going to get the guitar, and this is the tune here. As far as we can tell, this is a song that first showed up about 1500. There's a manuscript in the British Museum that is entitled Dame Whittle Waddle, and it's in Middle English. You know this as the Fox, okay? So if you don't know the Fox, you probably should. Oh, snowflake out on a chilly night, over the ocean of blue and white. Southern Cross is a guiding light and headed for South Polo. Polo, Polo, Southern Cross as a guiding light headed for South Polo. Over the albatross soaring through through. The penguins fly in the krill flecked blue. Seals and skuas, great whales too, all playing round South Polo. Polo, polo, seals, skuas, great whales too, playing round South Polo. 1 flakes a miracle, 2 a display, 3 and you might wreck your car today, but make a 2-mile pile and they're on their way, flowing from South Polo. Polo, polo, you got a 2-mile pile and they're on their way, flowing from South Polo. Oh, the physics is simple, all piles spread, water batter or caps on a bed, or a continent-wide 2-mile pile snow-fed and heading from South Polo. Polo, polo, you got a continent-wide 2-mile pile, snow-fed, heading from South Polo. Slow in the middle, thick and cold, down through the mountains, carved and old, picking up speed in the ice streams bold, don't fall in a crevasso, 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 picking up speed in the ice streams bold, don't fall in a crevasso. Ice streams at the sea don't make bergs right away. No, they flow across the ocean for many a day as a great ice shelf in a rock-bound bay with friction from the side. So, you got a great ice shelf in a rock-bound bay, friction from the side. So, if we raise CO2, warm the air and sea, melt the shelves away and let the pile spread free, it'll raise the ocean towards you and me. Well, it shrinks that 2-mile pile, 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 raise the ocean towards you and me, shrink that 2-mile pile. Oh, an Arctic fox on a chilly night at the edge of another ocean, blue and white. If we melt their ice, would that be right? Both poles are on the same trailo, trailo, trailo. If we melt their ice, would that be right? Both poles are on the same trailo. Oh, a snowflake out on a chilly night. So, thank you for coming. A true pleasure to see you all, and I hope we can do some questions. We will pop over to the next talk. I see Isabella Vallecania there. Hi, Isabella. We're looking forward to yours next time. So thank you. I will stop the share and we'll go to questions here. But make sure you come next week to hear Isabella.
Fantastic. Wonderful. Anyone got questions for Richard? Put something on the chat and we'll get you asking questions.
And thanks, Roger. Doyle and I had a good time. I was carrying, Roger has a note about Doyle Watts in Antarctica there in 1978, and he was doing sampling, and I was carrying his tool for his rock drill.
Much as I'd like to chat about him, I'll leave the chat to the scientists. But thank you once again. Clearly, musical qualifications are part of joining IGS, actually. So,
anybody with any science questions out there, or is everyone just so blown away by the what somebody's described as punk, I'm afraid, Richard? Or
boy, I'm getting old to be a punk. I got to tell you. Somebody's got to have a question here.
Pete Nino, go for it.
Yeah, thank you.
Hi, Richard.
Hi, Pete.
Great talk. Thank you very much. Hello from Scotland. It's a question about the bedrock and the till. So what length scales really matter for the sort of bedrock and till patterns that you're looking at in Thwaites? And yeah, so what would you be sort of most scared by in terms of dynamics? Is it just if it's, I mean, because it's clearly not totally covered in till from what you're showing.
Yeah.
So what are the length scales that you really need to know, and you know, what data would we need to get that?
Yeah, that's one of the things that has driven us crazy since time began. And it's, you know, so the kind of work that Rob Larder does and that Julia Wellner do in sort of mapping the bed offshore, the stuff people are doing under the ice shelves, the MELT project and those Tarzan project, and then the people going on inland. Hugely important. You've got to get the structure. So the big faults, the big bumps, the things that are resolvable geophysically. The models for basal stuff say that if you get the till out of the way, then most of the drag comes from things that you will never, ever, ever resolve. And that's this crazy problem that goes back to Weirtman sliding and so on. And so we just have to understand where you would get the till out of the way. As long as you got the till, all you have to worry about is there's a bump in the way and there's very little in the way of skin drag. There's very little tangential stress. You just have to get around the bump. And it's just, you know, a slippery Stokes flow around a sphere. But once you get rid of the till, then little bumps and little rocks in the ice, the stuff that Luke Zoot does of dragging rocks in the ice over the bed, actually become really, really important. And so it's, I think that the big thing is to keep Rob, to keep Julia, the people in between mapping the bed, and the folks get the swath radar going. And then it's going to just have to be understanding to drag, laboratory, analog, small glacier, because you're never going to resolve the 1 centimeter pebble that's actually providing the drag.
Thanks.
I see one from Rob there.
Yes, go ahead, Rob. Where is Rob Larter? Are you?
Yeah. Hello. I'm just trying to find the unmute button. No, so the stuff that Richard was just talking about, the real credit belongs to Kelly Hogan and particularly Rob Arthurn, who did some fantastic roughness analysis that really expresses the point that Richard was just telling about. But no, I was just going to say, right, Richard, you've scared us all to death. You know, there is this long tail. I think some of us know about this long tail, and you've made me more worried about it than ever. So what have we got to do to slay those dragons, to get ourselves back to believing the Ipcc predictions?
Yeah. I mean, and you know, you're a leader of part of it. And you know, we've got to get the, I think that we know the biggest questions, right? So you know, and again, we'll make it very clear, how much the algae growing on the edge of Greenland change the albedo and change the melting rate so it affects sea level is important. How much the surface mass balance and so on is important. We have to keep work going in all of these directions. But the biggest ones are, will you retreat from the sill if you force it? Will you retreat from the bottleneck? And that really is mapping topography, understanding processes, getting the bed right, getting the models up to speed. It is, I think, and this is self-serving because I'm a tiny little bit of a big project, but it's the International Thwaites Glacier Collaboration. I think that, and other things and other people and work that supports this from Greenland, because the understanding that comes out of Helheim and Jakobshavn and the other glaciers in Greenland directly and immediately informs that. So we have to learn those pieces. And then I think we just have to get better on fractures. And this is really contentious. Every time anyone writes a new paper on fractures, it changes our view, which means we don't have near enough papers on fractures. And so, you know, what does this one say? What does that one say? How high can the cliff be when a magnitude 5 earthquake happens because the front of the glacier fell off, how much does it damage what's behind it? This is hard. And it is, right? You do a little laboratory experiment and it tells you the ice is strong. It turns out that both Da Vinci and Galileo wrote about what they call the size effect, which is as you go to bigger pieces, it tends to break more easily. If laboratory measurements actually applied to the full scale, they would have had a really easy time finding a big piece of marble to carve beautiful things out of. Okay, so this idea of bigger things break more easily goes way, way back, but how much more easily? We're going to have to get that. And then I have just nagging in the back of my head this horrible thing, right? So I'm a geologist. I hung around with geophysicists. I have a graduate level minor in metallurgical engineering and materials science. And some of you have heard this story. I took the broken things course. And the professor would bring in broken things and show them to us, and then we'd discuss why they broke. And at some point he said, calculate everything to 5 significant figures and then make it 3 times stronger than that, because you'll never get it right to a factor of 2. You'll never get it right to a factor of 2 because you can't know everything. And we're within a factor of 2. And so there is this question: if you go back to the sort of economic models that Nordhaus and company run that say that we are hurting ourselves economically because we're not dealing with climate change, they usually have some level of damages, some level of sea level rise, and some level of damages from those sea level rise. If you gave them a full PDF that includes the tail of the dragon, and you integrate it over the whole probability density function of sea level rise, and then you said probably, because as the sea goes up, the costs go up faster because nuisance flooding becomes expensive, and so you integrate it over the costs. I am pretty sure what happens is that the value of limiting CO2 emissions goes way up. The social cost of carbon is way higher than people are estimating if you properly include these tails. That is my belief. I have not run the integrated assessment model to demonstrate that, but it is my belief that if we properly include what we know now, that you would say the social cost of carbon is really high, the value of heading off CO2 is really high, and the value of funding more of those bright students and early career researchers to get at this is way high. In the US, primarily, we've had heroes, the people, and I mentioned Julie Pellet is online. She's a hero, okay? She's a huge hero, and she did great things for us. But NSF is still primarily funding research of this out of what they call core budget. It's not an initiative. It's not big new money. You know, ultimately we're competing with penguins for funding. My suspicion is the value of funding the students and the early career researchers in this field is off the scale, and the cost of what they do is pitifully tiny compared to the cost of the damages of meters of sea level rise when we're expecting tenths of meters of sea level rise. There's an editorial, okay? That's a serious, serious, serious editorial. I can't justify that the money would be well spent, but you know darn well it would be.
Yeah, thank you. Fantastic.
Any further questions for Richard? Just type onto the chat.
What about East Antarctica? Yeah. Hi, Helen, how you doing?
Hey, Richard. Great talk. Loved hearing you singing. My daughter came and heard as well. It was wonderful. Thanks.
Hi.
I just had a question. You spent a lot of time talking to us about sea level and uncertainty, and it was really well. I really enjoyed it. I do want to know what you're thinking at the moment about East Antarctica.
Yeah, I think it's harder to kick East Antarctica out of the bottlenecks, and I hope that's true, but I don't think we're sure. And it's very, very clear that West Antarctica is weeny compared to East Antarctica. If you actually dump the the Aurora and Wilkes basins and the other basins around there, then it gets really, really serious. And you know that they have been dumped. You know that there has been retreat there in the past with pretty high confidence, not absolutely sure, but it's likely. And you know that they are seeing thinning at the mouth of some of them. And there are some really deep channels running back under them. I personally, you know, I was plugging the International Thwaites Glacier Consortium, but I suspect that a level of research like that against Totten and a couple of other those glaciers is highly, highly warranted. And you can add something to that if you'd like. I suspect you would agree, but if you want to add, please do.
Oh, no, I absolutely agree. East Antarctica keeps me up at night.
Yeah, that's the real, because West Antarctica's low. You know, it can't raise sea level a huge amount because it's only 1,500 meters above flotation at the top. East Antarctica is way up.
Yeah. Thank you.
Thank you.
Tim Bartholomew, go ahead.
Yeah, thanks, Richard. I guess my question is, you know, given all of the uncertainty that you talked about, if you had your druthers for the next IPCC report, how would you forecast sea level rise? What do you know, how are you going to actually put numbers on there that are going to reach international consensus and inform policymakers?
Yeah, I honestly think that the fourth assessment came close to doing it right. Now that's self-serving because I played more of a role in the fourth assessment. I was not in charge. No. So, but that they said that it is, we can quantify mountain glacier melt. We can quantify thermal expansion of the ocean. We can quantify surface melting in Greenland. We can quantify mass balance changes, including more snowfall in Antarctica. Those give a well-quantified, well-understood, actionable set of numbers. And then there's this tail of the dragon. And if you think that we're going to miss it, then use the quantified part. And but we can't yet provide really, really good guidance on whether it's going to get us. And you remember the fourth assessment, the sea level chapter says there is no basis in the refereed scientific literature to provide a best estimate or an upper bound on sea level rise. It's almost those words. That turned into a table in the summary for policymakers that says projected sea level rise excluding future rapid dynamical changes in ice flow. Model-based estimate, right? Excluding future rapid dynamical changes in ice flow. I think that was the accurate statement, but it's not actionable. Right? It is hugely important in mitigation decisions. It is hugely important in research funding decisions. It is not actionable for a coastal planner. And that's the kind of thing that keeps you up at night. And when we were discussing this back in the fourth, we went around and around and around and around on that issue, that people are counting on us to give them good numbers. Well, what do we do? And like I say, I could throw rocks at people who didn't start an initiative on this and support a new generation of researchers a generation ago. I think we have grossly underfunded the research, and I think we should be able to do actionable things now, but I'm not convinced personally that we really can. And if you'd like to add to that, Tim, you clearly have deep insights too.
No, well, thank you. No, yeah, it's a conundrum, and I'm not sure when, you know, the best we've got is, well, it's the knitting together of the models and the paleo observations. So I think that's the challenge.
There you go. Thanks.
We have a question from Julian Williams, but he says his internet isn't great. So he says, what do you think about the influence of the Arctic on sea level rise? From what he understands, the maximum temperatures exceed those in the Antarctic. Do you think sea level rise input is greater from the south or the north?
Yeah, right now it's Greenland is, so mountain glaciers in Greenland are more important than Antarctica right now, is my understanding. And you know, for the Arctic, there's some stuff up in the Russian Arctic. A lot of the Canadian glaciers. The Canadian glaciers are great labs, as well as Greenland and Svalbard is great labs. And you can learn so much from those places that it's really exciting. Greenland is going to be important. There's no question about it. Fascinating new work coming out on these cosmogenic isotopes in the history of Greenland deglaciation. We make it warm and it's going to melt, but it's less likely to do these crazy fast things. If you start building and saying we're going to think about more than 100 years, we're going to think about 150 or 200 years, Greenland's huge. Out to a few decades anyway, I think our ability to project Greenland is fairly good. Not perfect, more work is needed, but I think our ability to do that's fairly good. Our ability to project the Canadian Arctic glaciers is fairly good. But there are these glorious laboratories that you can go to Ellesmere, you can go to the coast of Greenland, you can go to Svalbard, and you can learn stuff that it's a lot easier to get to those places than it is to get to Thwaites right now. So.
Okay, thank you, Richard. I think we've run out of questions there. So say a huge thank you again, and also advertise next week's talk from Isabella Velkovna. So I don't know if everyone wants to unmute and hide their videos and say thank you very much to Richard, because that was an absolutely fabulous talk. It's been really, really wonderful.
Thank you.
Hey, thank you. Wonderful to see you all.
Thank you, Richard.
Yeah, thank you very much indeed. And there's lots of thank yous on the chat as well. That was absolutely wonderful.
Good talk, Richard.
Hey, thanks, Julie. Good to see you. Take care.
Yeah.
See you all next week.
Yes, be here. Don't miss it. Isabella's great. Got to hear that.
Okay.
Thank you.
Thanks,
Good night.